Yeah, so my name is Oliver Schroeder. I'm in the HPC services and software team at Science and Computing. We are a IT service and software solution provider for complex computing environments, as it actually says here on the slide. We are about 300 people working mainly for the automotive industry and have offices all over Germany. We're a daughter of Bull, and so today I'm going to talk about runtime performance optimizations from OpenFOAM Simulation. It's not work that I've done myself, but I'm basically presenting work of a colleague. And so we start with the thanks. So most of the work that I'm going to present was done by my colleague Christine. We got some help from the applications and performance team at Bull, France, Madeleine Richards and Rafael Mendez. And then we had a lot of discussions with Josef Hellerer, so thanks for that too. So here's the structure of the talk that I'm going to give. I give you a brief introduction why you should be interested in what I'm going to talk about. Then I'm going to skip over the test case because it's only in the overview but not on the actual transparencies. I talk a bit about benchmarking environments so you can see what we use to run the simulation, and then I give you some initial results that were the actual starting point for the investigation, because the initial results were not what we expected. And that drove some of the investigations later on. So we looked at a couple of dependencies. So we looked at the CPU frequency, at some things with the interconnect, and we looked a little bit at the influence of the memory hierarchy. But the methodology is very different from what we saw in the talk before from Pak, so I think it'll be interesting. And then I'm going to talk a little bit about performance improvements that we can get, namely by looking at the API communications and at the domain decomposition. And then I'm going to draw some conclusions. So our starting point was, well, how can we improve application performance, especially by not tuning the application itself. Because where we come from, often we have to do benchmarks for tenders, and they're often either it's ISV software that you can't touch yourself anyway, or if it's open source software, you're not supposed to. So what can we do then? Well, first of all, we can use the resources that we have efficiently, or we can, and second of all, we can select appropriate resources. But for that, we need to know, well, what are the appropriate resources or how can I utilize them. So we need to analyze the behavior of the application, and then we need to tune the runtime environment, which contains many moving parts. So in this study, we're looking at a specific OpenFOAM test case, which I can't share because it was provided in context with a tender. And so we're tuning API communications, and as I said before, domain decomposition is something that can also change. The test environment that we had consists of two different test classes that we had from Bull. One is called SID, the other one is called Robin. And so I've tried to, so a lot of things are similar and some things are different between the two test classes, and I marked the things that are different. So they are all Bull blade systems that have two processors. So in one case, it was a 10-core Ivy bridge at 2.8 gigahertz, and the other one a 12-core system at lesser frequency, 2.7. Then cores per node are obviously different as well, 20 and 24. Very important, the level 3 cache is different in both cases, so I will reference that point again and again throughout the presentation. So we have, with the 12-core version, we have 5 megabytes of L3 cache more than with the 10-core version. Obviously, it results in the same L3 cache per core, but the overall cache is different. So then we had 64 gigabytes of memory, 1866 megahertz. We, as an I/O file system, we used NFS over IB. We had an FDR interconnect, so that was the same for both systems. Also, the software was mainly identical. The only difference was a version difference in Slurm, which hopefully doesn't impact our results at all. So we didn't take that into account. So we looked at OpenFOAM 2.2.2. We used Intel and GNU compilers. Well, we used 2 different versions of MPI. So we had an Intel MPI and a Bull MPI, which is a specifically modified version of OpenMPI. And as an OFAT, we had the version 1541. So, the first thing that we obviously did was, well, how does the Intel compiled version of OpenFOAM compare to the GNU compiled version? And we looked at different sizes of our problem. So we usually had 16, 32, and 48 nodes, and it's 16 tasks per node. So fewer than we could do. We could do 20 or 24, but we only use 16 per node. And you see, so this is the wall clock time. So lower is better. So consistently, the GNU results are a bit better than the Intel results, though we use the same Intel MPI in both cases. Well, mainly this has to do with that OpenFOAM development usually employs GCC. Maybe they have some tunings in there. We didn't investigate this any further. We just stuck with GNU C from here on. The next thing which is interesting is, well, I have, so these investigations are on SID, so I have 10 cores per CPU, and is it better to use all the cores or should we use fewer cores? So we looked at 8 versus 10 tasks per CPU, and what you see here is, so blue are the 8 tasks, and again lower is better. And the eye already tells you, well, it seems to be getting better all the time, and especially, well, the 8 tasks are consistently better. Well, there are 2 reasons, well, actually 3 reasons why that might be. So if we use fewer cores per CPU, then we have more L3 cache per core that we can use. And we have more memory bandwidth per core that we can use. So these are 2 reasons. And the last reason is that we have a different domain decomposition for the 2 cases. And that can also impact the performance. And then, well, we did a similar investigation with StarCCM, which my colleague presented at one of the last HPC advisory councils. And well, if you have a successful model, then you stick to that. So and the very important thing there was to study CPU binding. So we did the same thing here. And we have, with no CPU binding, we have 1801, and with CPU binding, we have 1799. And it basically sticks the same whatever number of nodes you have, so this is rather puzzling. The next thing we looked at is, okay, let's use different InfiniBand fabrics. So we used the DAPL or OFA with the MPI. We looked at zone reclaim, we looked at transparent huge pages. We switched on hyperthreading, then we doubled the number of tasks. And we looked at the turbo boost, and you see nothing really very interesting happens here except for the hyperthreading, which is a disaster. And if you compare this to our results with StarCCM, then this looks really, really different. So this is what happened with StarCCM, where we switched from nothing to CPU binding, which was consistently high effect even up to here. So that what we get from here is, well, CPU doesn't seem to play the largest role, and it's not really the bottleneck of the computation. So because the system has other problems, it can't really utilize what it's getting from the CPU. And you can see that especially up here. So usually you would expect some sort of decrease in the wall clock time, but there's nothing really there. So where's the system spending its time? Well, there are other things that we can look at. So the first thing is that we look at the interconnect. And what we do is, so altogether we have 3 different sorts of configurations, and 2 of them are on here, and the 3rd one comes on the next slide. So what we do is we start with a fully populated system. So we have 20 tasks per node, and then the next thing that we look at is what we call compact, where we only have 10 tasks per node, but all 10 tasks are on one CPU. There's another one which we call scatter, where we also have 10 tasks per node, but there are 5 on one CPU and 5 on the other one. And the reason for this is that we want to see, well, what's the influence of the interconnect without but the cache that the tasks have and the memory bandwidth, it stays the same. And so we compare the fully populated now 320 tasks on 16 nodes with 320 tasks on 32 nodes, and what we get is, well, a speed up of 3%. Okay. Then we look at 640 tasks on 32 nodes and increase that to 64 nodes, and we get a speed up of 11%. So that's interesting because again we have 2 competing phenomena. Namely, on the one hand, you have basically doubled your network bandwidth, but also you have some. So that should be good for because you have to double the amount of nodes. You also have a bit more overhead because now you have some communication that needs to go over InfiniBand that went over shared memory before. So these are 2 effects that are opposing each other, but you can see the increased interconnect bandwidth gives us this 11% improvement in runtime. So that was the first bit. The second bit is now we compare the compact version and the scatter version. So all 10 tasks on one CPU or 10 tasks distributed among 2 CPUs that we have. And here the effect decreases with the number of nodes. So with 320 tasks we get a 50% speed up. And with 640 tasks, we get only 28% speed up. So we could argue here that the memory hierarchy is less of a bottleneck than the interconnect as the number of nodes increases, which is not really completely contradictory to what you would expect. But I said before, we have 2 different effects from the memory hierarchy. Namely, we have more cache, we have twice the amount of cache, and we have an increased memory bandwidth. And we try to decompose which is which. So we looked at performance counters to see the improvement, the actual used improvement in memory bandwidth. And you see here, so of the 50% speed up that we have, 28% are due to improved memory bandwidth at the 32 node case. If you go up to 64 nodes, only 4% of that is utilized. The effect from the increased cache basically stays the same. So here we have 22 and here we have 24%. Yeah, I mean, since the memory that each task needs, because you have twice as many tasks here as you have here for the same problem, the memory throughput isn't as crucial anymore. And now the main problem that's left seems to be the interconnect. There's a last thing that we looked at, namely, does file system I/O is that important? But it's not. So we looked at different Lustre configurations with different stripe sizes and different number of stripes and so on. And so here you can see 16 nodes flat, 32 nodes basically flat, 48 nodes flat. So so that's just for completeness, and we did the investigation. So but that's not really an issue here. Now, what can we do to improve our performance? Well, we can do first a little bit of profiling. Let's see how much time do we actually spend in MPI communication. And so again, we compare 320, 640, 960 tasks, so 16, 32, 48 nodes. And what you see here is, so this is the time spent in user code, and this is the time spent in MPI code. And you see it increases dramatically as a share of the complete time. So then the next thing to look at is obviously, so what kind of routines make up the time in our MPI calls. Because if we're lucky, it's just a few, and we can tune those maybe and then gain something from it. And actually it turns out, yeah, well, MPI all reduce basically 50%, whatever the size of the cluster. The next one is MPI weight all, 30%, and then we have 20% other stuff. But so it's worthwhile to look at the MPI all reduce. And what you can do with with inter-MPI is you can actually say, well, there are a couple of algorithms that you can use for all reduce. Altogether there are 8, so there's a recursive doubling algorithm and yeah, reduced and decast and so on, Raben-Seifner's algorithm and so on. And you can just tell inter-MPI, well, use this algorithm or use this other algorithm. And we looked at that for 320 tasks and 640. For 320 tasks, there isn't really much of a difference. You see that the default actually is already pretty good. So in the measurement that we made, it actually gave us a better number than what we got from the best algorithm that we could choose. But for 640 tasks, again, the binomial gather and scatter algorithm here was the best, and it was significantly better than the default algorithm. So we gained 11% by just setting an environment variable. So that seems to be very useful. The last thing that we can look at and easily tune is the domain decomposition. So the default that you have is 2, 2, and then number of nodes divided by 4. So this is why this is our reference number. So this has 1, and we tried a lot of different domain decompositions. You can see you can do it really badly and lose a lot of performance. You can also do it well and have like a reduced runtime by like 10%. The same is basically true here. The improvement that you get is overall is less, but you can, yeah. Well, I mean, if you do it really badly compared to really well, it's again a difference of 10%. So choose it domain decomposition wisely. What we take from this is that what you want to do obviously is you try to communicate less, so you don't have the interconnect bottleneck to fight. So if you can improve data locality, that's good, but well, if the inter-node communication overhead, if that increases here from the from 16 to 24 nodes, then of course this advantage gets reduced. Then the last thing that we did, and this is not an entirely fair comparison, is we compared Bull MPI to Intel MPI, and here we we just use them as they come out of the box. So it just goes to show that there can be a difference in MPI, and the improvement, it decreases as you go from the default decomposition to the best one. So if we just had taken the default domain decomposition, it would have been 3 or 6%. But then when we took the optimal decomposition, then this advantage was reduced, as is obvious from our interpretation that we had before, because it improves data locality, so the influence of MPI better be a bit smaller than it was before. Yeah, that's basically all I have to say for Bull MPI. So the conclusions that we draw from all this is, well, the CPU frequency and thereby the dependency on the CPU isn't all that great with OpenFOAM. Cache size is an important thing, no matter how big your cluster basically is. The thing that's really not very nice about OpenFOAM is that the bottlenecks change as you change the cluster size. So in the beginning, you're limited by, if you have a small cluster, you're limited by memory bandwidth. If you have a large cluster, you're limited by communication. So there is no real ideal way that you can say, well, choose a really small cluster, choose a really large cluster. Sometimes if your cluster is big enough that you don't run in any of your bottlenecks, then you can just increase your cluster size and the computation time goes down, but here you're bitten by one or the other problem. Tuning MPI or reduce operations is really fruitful because you get 10% by setting an environment variable. Domain decomposition is also useful because there again you can mess up or gain something of the order of 10 to 20% from worst to best. And the file system doesn't really have a big impact at all on our results. So that's basically all I have to say. It was a bit faster than I was expected to. So okay, questions?
Yeah, I have a question. Is there a possibility to run the same set of the tests related about the latest available in Decomposition? Because the version you had used is 1.5 years old, and you're running it on the modern hardware using isolation, for instance. So I would recommend to try the same things the latest available, the latest you can try. Because the default settings, they are very independent, and if you use the old version of the info interface, not the latest hardware. It's one point. And another thing is that then you are trying to figure out the impact of the L3. I guess that you are trying to figure out cache misses. I would recommend you to use MU and available and use or something like that.
So I mean we looked also at cache misses, but we did that also with DAO-CCM, but it's not really, how should I say, with the memory bandwidth it's really obvious how it translates into your compute time, but with the or your runtime, but with the L3 cache misses it wasn't really that obvious. I mean the number of cache misses obviously decreases as when you have more cache, but the numbers they didn't tell us so much. So, but thanks for bringing that up.
Yeah, and in case you have you see strange behavior in production code, it would be great if you can hack someone from the maintenance of that project. So
yeah, but this
solve the problem.
Yeah, but I mean here the strange behavior that so I mean OpenFOAM obviously.
I mean that you see that the default behavior out of the box is not sufficient from your point of view. We'll be glad to handle it.
Okay. Oh, thanks. Other questions?
One thing I noticed is, so you show the compiler options, but we're not using something like Xhost for Intel or the native architecture thing for GCC, so you're not really targeting the platform you're building on. Is there a particular reason for that? Because so if I'm not sure if was it Standing Bridge?
No, it was Ivy Bridge.
Ivy Bridge.
Yeah.
But with these compiler options, you're not generating ADX, for example.
That is true. Yeah, Joseph, you have a comment on that?
There was a difference between GNU compiler and ICC, about 5%. The GNU compiler was better than Intercompiler.
The compiler options shown were not generating ADX instructions.
When?
They were not telling the compiler to generate ADX instructions.
There was there were two variations between GNU compiler and Intercompiler, and the GNU compiler was better about 3 to 5% performance.
On the first slide where you showed
Yeah.
the compiler, showed the info text and were the flags the same, or
As far as I know, yeah, they.
So my point is they should be the same.
Okay, well then I would have to get back to the people who actually did the compilation. This is the information that I got from them.
One other question. So I thought you were not able to talk about the actual input that was used because of the temperature situation. But so I'm a little bit surprised that you say that I/O doesn't make a difference, because OpenFOAM tends to be very sensitive to the I/O, and since you're running on NFS over IP, I would be concerned about that.
Well, yeah. So
You show that you were tuning lusters.
yeah. So the main thing that we did was NFS over IP. But when we did the luster part, we also had a luster system for storage.
Over. Okay.
Yeah. No, that's a separate system that we used only for that test. I'm sorry, I wasn't clear on that. Yeah.
Yeah, I know that you're good presentation. I know that you're not allowed to say more about the input file, but which software in OpenFOAM that you're doing it with? Because different softwares can kind of have different characteristics, and you show that all the users use a lot on your particular one. So I'm just curious to see which one you use.
So, Joseph, do you remember which solver that was?
Yes, it's PimPerFOAM.
PimPerFOAM?
Yeah.
Okay.
Okay, thanks.
PimPerFOAM.
Yeah, so maybe I should say that. So thanks for bringing that up. Also, I want to mention that in the beginning that I mean what I'm showing here is it's a specific model with a specific solver. So your mileage may vary, obviously, and the main thing. I'm not trying to give you overall best practices for OpenFOAM. Just investigations that you can do, and if you have a lot of repeatable workload, then you should do on your own system. Obviously, I'm just trying to show what kind of investigations might be useful and which are available to you if you know about them. So it's not so difficult to figure these things out on your own system. So yeah.
Any other questions?
Okay, well, thank you.
Okay, thank you.